Okay, welcome back. So, at the end of lecture yesterday, I had mentioned this specific application of Cauchy-Gorsat, which is the following. Um, a function that's analytic through a simply connected domain must have an antiderivative everywhere in that domain. So this had a really quick proof. This proof was exactly by applying Cauchy-Gorsat and then noticing that, oh, we actually have this. So we applied our slightly modified Cauchy-Gorsat that was modified for not just simple closed contours, but actually any closed contours if we were on a simply connected domain. And so um, we had this condition that along any closed contour in a simply connected domain for an analytic function, this contour integral was 0. And this is exactly that last condition in that list of equivalent conditions in our big antiderivative theorem, right? This is our condition 3 here, right? And so this condition 3, since all these are equivalent, this implies 1, which is that it has an antiderivative throughout the domain. Okay, and that's how we proved this. A further corollary is since the plane itself is simply connected, then a function that is analytic throughout the entire plane, that is an entire function, has an antiderivative. Okay. Now this notion of simply connected here is definitely required because there's an easy counterexample if this thing is not simply connected. So here's a counterexample. Suppose f of z is analytic on a domain D that is not simply connected. Okay. Then we have an easy example, or I should say we have an easy counterexample. And this is kind of a key counterexample. In a sense, this is like the only, I should say the only counterexample, but it is, in some sense, the main and most important counterexample, because basically any setting that we're in where this thing that we're talking about fails is due to the failure of this example to have an antiderivative. Okay. So the easy counterexample, to guess what it is before I even write it out. Remember, at the beginning of yesterday, we dealt with uh, a little annoying thing that we had to manage, which was what to do when we're integrating, say, 1 over z, right? And we had to do this, right? We had to worry about this fact that we have to make a branch cut somewhere, and so if we have any closed contour like this, say about the origin, then we couldn't avoid missing that branch cut. Okay, and we had to do some special things in order to actually calculate this integral. Okay, now we were able to ultimately calculate it, and of course we found that it was not equal to 0, right? That integral was equal to 2 pi I. And so our easy counterexample is exactly that. If f of z is 1 over z, okay, this thing is analytic on the entire complex plane except the origin, right? So let D be the entire complex plane minus the origin. So complex plane with the origin deleted. Okay. So f of z is analytic on D. Okay, so it has an antiderivative, say on this region D, or I shouldn't say that. Um, I should say that it um, it is it's analytic on D, but D is not simply connected. I shouldn't say what I just said yet. So D is not simply connected. Easy way to see this, of course, is if I actually draw in this picture. This is the entire complex plane with the origin deleted. So we have all points except the origin. And so while in our definition of simply connected, there's a closed contour that doesn't contain any points outside of D. Okay, but any contour that wraps around this hole is going to contain a point that's not in D, namely the origin, right? This intuitively is exactly what we have to keep track of. Going forward, you're going to see that, like, keeping track of the contours wrapping around these holes in the domain, which we are going to view either as, holes in your domain, or it is points where the function in question is singular. And so those holes have to be made in order to be able to talk about the function, or at least talk about where it's analytic. Okay. So D is not simply connected. There's an example to show why. Here's a closed contour that goes around a point that is not contained in D. Okay. But notice that this fails, right? This fails our Cauchy-Gorsat, first of all, right? So note this fails Cauchy-Gorsat. Because we already computed that, say, if we look at this, if we consider this our curve C, we know we have this hole here, and we computed yesterday that the integral along C of f of z dz, that is the integral along C of 1 over z dz, was 2 pi I, which is not 0. Okay, it's not 0. What else can we say? Well, what about this statement of having an antiderivative? So, does f z equal 1 over z have an antiderivative on D? The answer, no. No, it doesn't. Okay, for the exact reason that we went through in yesterday's lecture. Okay, so big F of z that we define in the usual way, right? So this big F of z being ln of r plus I theta, where we have to choose a branch. This is not an antiderivative of f on D. Exactly because of this ambiguity of the branch cut that has to be made in order to define this thing. It's not only is it not analytic as is required there, it's not even defined, right, along those points. And so this is not an antiderivative of f on d. Okay? And so it fails Cauchy-Corsot, as we saw, like I said, when we computed that integral yesterday. And it's not that surprising then, since this fact about having an antiderivative required Cauchy-Corsot, right? That's how we proved it. Okay, and so you have to be careful when you make these claims. So let's go back here. So then this statement that a function that's analytic on a domain has an antiderivative, it is very much needed that the domain in question is simply connected. Okay, so domain's got to be simply connected for this statement to be true, and that's because we can apply this Cauchy-Corsot in this case. Okay, so a function that's entire, that's analytic on the entire complex plane, has an antiderivative because the entire complex plane is simply connected. And this statement that you really want is true if you're talking about a simply connected domain. So keeping track of the holes in a domain is extremely important. Okay. In fact, that is going to be exactly what we have to do here going forward, because you are going to want to talk about instances where a function that you're interested in is not entire, right? It's not analytic on the entire complex plane, and it's not analytic on some simply connected domain. It's actually it is actually it has some singularities. So in order to talk about a maximal set where it's analytic, we have to take out some points, okay, which is going to make it not simply connected. But, of course, that raises a good question, which is, what do I do when my domain is not simply connected? So, immediate question that comes out of this is, what do I do when my domain D in question is not simply connected? Well, the answer is we apply Cauchy-Corsot to multiply connected domains. So what does multiply connected mean? Well, multiply connected is just not simply connected. Okay, so quick definition of multiply connected. A multiply connected domain D is a domain that is not simply connected. Okay, so then you might notice here that really I haven't answered this question. What do I do when my domain's not simply connected? Well, I just come up with a word that means not simply connected, and then I do stuff on that. But that doesn't really tell you what it is I'm doing. What I really mean by this is that we are going to have a way of making Cauchy-Corsot work on a multiply connected domain. You might already try to, think about how to do this, or how to deal with this geometrically. Okay, and so there is a really, really nice picture that comes up here that kind of starts to explain some techniques that you might use to deal with domains like this. And so it turns out we can make a version of Cauchy-Corsot work on such domains, though it is a little different. It is a little different from the original statement. And you know it has to be different because I came up with this counterexample, right? You know that this new Cauchy course that we're applying is not going to suddenly magically make, say, this function on a multiply connected domain have an antiderivative necessarily, right? Because we just found one that didn't, right? 1 over z. 1 over z is a great thing to keep in mind as a very, very simple counterexample to a lot of statements that you want to make. So, so 1 over z, great counterexample here. And this is not going to fix that. But it is going to say that we have a version of Cauchy-Gorsat that's going to work in this way, and this is a pretty nice thing that we're able to do here. So let me state this theorem. And then I will draw a picture that illustrates how it is we would go about proving this. Okay, so you know the following theorem. This is Cauchy-Gorsat for multiply connected domains. This is at least our third version of Cauchy-Gorsat. So Cauchy-Gorsat for multiply connected domains. Okay, so we have two assumptions. So suppose that one, C is a simple closed contour. Positively oriented. So that means oriented counterclockwise. Suppose that C sub k, okay, for k equal to 1, 2, 3, all the way up to n, so k is some natural number up to n, are simple closed contours interior to C, oriented clockwise okay, so the opposite orientation to C. And they're disjoint so none of these curves touch any of the other C sub k's. They're all disjoint and whose interiors have no points in common. Okay, I'll draw a picture here in a second. If a function f is analytic on all of these contours, and throughout the multiply connected domain, that consists of points inside C and exterior to all of the C sub k's. Okay. Then the integral over the outer contour C of f of z dz plus the sum from k equals 1 to n of the contour integral over each c sub k of f of z dz is equal to 0. Okay. take a second to have a look at that. What do you notice? So if you already got the picture in your mind, this is saying that if I take the contour integral along the outside curve and add to it the contour integrals along each of the inside curves, they cancel out like this. Let's draw a picture to see how this works. And when I draw the picture, I'm going to give an example of kind of a context where you're going to likely see this, right? Or exactly where you're going to see this. So let's say we have a function f, and this function f here, I'll draw my axes and I don't care that much. This function f, we'll say, is analytic on a domain that is enclosed by a curve that maybe looks like this. Okay, so here's my curve C. That's a simply closed contour. Okay, so this is simple closed contour. All right. Now, if we have a function that is analytic on C and all points interior to C, then we have just normal Cauchy-Corsat. Okay. But let's say that it's a little bit more complicated than that. Okay. Say that we have a function and it's analytic on most of this. Okay, but there's some problem points, right? So we are going to address the idea of poles of a function or singularities of a function, how to deal with them specifically, and we're going to have a really, really beautiful theorem called the residue theorem. That's kind of the crowning achievement of this course. It's going to be our main goal in this course, even if you don't know it, is to get to the residue theorem and use the residue theorem on a bunch of examples, and then we'll basically consider ourselves done with the course, because that's kind of like the last part. That's what we're aiming for here. Okay, and so the setting that I'm about to talk about is something that's going to come up a lot. And so say we have some points here. So let's say we have some problem points here and here. Okay, and so F is analytic on C and points interior to C, except at these points. Okay, except at those points. Well, even having a couple of points, right? Even satisfying this a couple of points, or everywhere except at a couple of points, you might say, oh, but I'm so close, right? I'm so close. I satisfied at infinitely many points, but I fail just at these two. So, maybe I can, like maybe not all hope is lost, but even just failing at these two means you can't use the Cauchy-Corsat that we've used up until now. And so what you can do is you can think about, okay, so I have a function that's analytic on C and the interior of C except at these 2 points. Let's cordon off these points with other curves. So maybe I'll call them C sub 1 and C sub 2. So I have created kind of an exclusion zone around those points, okay, using these two curves, C sub 1 and C sub 2. Now, let's say that I have the setup I indicate in the theorem. So I have my outer curve that is oriented positively, so it's oriented going counterclockwise. And let's give these interior curves that I've drawn here orientation going clockwise. Yes, clockwise, sorry. There we go. The opposite direction here. Okay. So now what I have is a domain where the f in question, right? I was talking about a function that was analytic on C and at all points interior to C except these 2 problem points that I've denoted in red here. Okay. Well, if I've sectioned those off with these curves, what that means is that on this domain that I am shading here, my function f is analytic at every point in the domain, on this outer curve, and on the interior curves. Okay. And so, in our version of Cauchy-Goursat here applied to this curve, the contour integral of such an f along this outer curve C plus the sum over the contour integrals of C sub 1 and C sub 2 of f, that's equal to 0. Okay, in this setup. And of course, you could draw a general picture where you have n of these points that you're sectioning off here with these curves. Of course, you know, if you look at the picture in the textbook, you might not even see these points drawn in. I'm just showing you where this comes up. Okay. So now the question is that one, you might have a question about the orientation. So the way that we've done the orientation here is in a way that the direction of each path of integration basically is done in such a way that the domain that you're integrating over always lies to the left. Okay, so if we think of ourselves going along this outer curve, the domain is always to our left. Okay, if we think about ourselves going along the inner curves, the domain is always to our left. Okay, can you formulate this in a way where you keep the domain always to your right? Absolutely, of course you could do that. You just got to pick, right? So you got to pick some orientation to be what you're calling the positive orientation. So this is the way we've chosen, but you could absolutely do it the other way. But you got to be consistent, right? So these have to have opposite orientation, or this cancellation won't work. Okay. So how do I prove this? So I'm not going to go through the whole proof of this. This is more of like intuitively how this works. The idea is that I want to apply Cauchy-Goursat somehow. So I want to apply the Cauchy-Goursat that we're used to somehow. What do I do? Well, basically, I create paths that connect these inner paths to the outer curve. So I add in these paths. Okay. So I add in these paths, say L sub 1, L sub 2, and L sub 3 in this case. Of course, we would need to add in more of these if we had more of these interior curves. And then I think about splitting this curve C, right, where these paths I've added intersect my outer curve. And so we've called this C sub 1 and C sub 2. I believe your textbook calls this top curve like gamma sub 1 and this bottom curve gamma sub 2. And we do the orientations in such a way where when we are going around gamma sub 1 and we get to this point and we're going to go around here, we would have basically the curve oriented in such a way that this orientation stays consistent. Okay. But that's only when we're going around this curve, gamma sub 1, that we'll define not just to be the outside of C, this upper half of C, but will be defined to be this entire curve here. And notice that we've done this in such a way that this orientation is consistent. Similarly, when I'm going around the bottom curve and I go on these paths that I've added in, my orientation is going to go the other way, and that also keeps the orientation consistent. The idea is we use Cauchy-Goursat on gamma 1 and gamma 2 in their interiors. Because now we have defined curves that enclose simply connected domains here, and we've defined them in such a way that this orientation is consistent in our picture. and this lets us do it. Okay. All right. And basically what we get here is because we are taking two paths, right? Geometrically, we have these paths described here, but when we talk about orientation, we have the path L sub 1 with that orientation and the path L sub 1 going in the other direction. When we try to do all these integrals, what do you think is going to happen? Every time you have an integral along, say, L sub 1 of whatever, you are going to have to consider the integral along minus L sub 1 here, right? And of course, the integral along minus L sub 1 is minus the integral along L sub 1 of the same thing. And so these cancel. So these integrals cancel when I'm summing, right? When I break up the sum along these parts of the curves, all of these L sub 1, L sub 2, L sub 3, those all cancel. And so what am I left with? Applying Cauchy-Gorsat here, I'm left with the integral over C of f of z. That's the outside, right? That's this part and then this part together. That's the integral over C. Plus, the only other curves that don't cancel out is integral over C sub 1 and integral over C sub 2. And that has to be equal to 0 because we've applied Cauchy-Gorsat. Cauchy-Gorsat says the integral over this whole curve, complex here has to be 0. And so that's it. That's how this works. So the reason I wanted to show you this picture is that this is something that this kind of thing is going to be a thing that you do often when you're doing some examples of these things in this course. So that is the reason. I wanted to make sure that you'd seen this. If it helps you remember how you would go about proving this thing from regular Cauchy-Gorsat, then that's just icing on the cake. Okay. So there's a corollary of this fact that is really, really nice that gives us what's called the principle of deformation. Okay, and so a corollary of this previous theorem is called the principle of deformation. And this is a really, really nice fact. Okay, so this corollary called principle of deformation. And it tells you that if you have two curves and one of the curves can be continuously deformed into the other curve, okay, we'll give some examples of that here in a second, then integrating along contours described by those curves gives you the exact same thing. If your function is nice enough on the region in question. Okay, so maybe it's not exactly clear what I mean by that, but let's let C sub 1 and C sub 2 be positively oriented. Simple closed contours where, say, C sub 1 is interior to C sub 2. If a function f is analytic in the closed region consisting of those contours and all points in between, then the integral over the first contour of f of z dz is equal to the integral over the second contour of f of z dz. Okay. Okay. How can I talk about this? Why does this work? So, quick proof. Let's draw a picture. So, we have a picture. We have an outer contour, C sub 2, positively oriented, so it's counterclockwise. So this is our C sub 2. We have an interior contour, C sub 1. It's also positively oriented. Okay. We have a function f of z, and this function is analytic on both of these contours and all points in between. Okay. We want to apply this modified Cauchy-Goursat for multiply connected domains. Okay. But actually, are we in a position to do that? Well, let's think. So, are we in a position to do this? Well, we have a simple closed contour that's the exterior contour. The interior contours are not oriented in the opposite direction. So we have one interior contour here. It's not oriented in the opposite direction. It's oriented in the same direction. Okay, so we'll talk about that in a second. But everything else is satisfied. We have a function to analytic on all the contours and throughout all the points in between the contours, right? We don't have to worry about the interior contours being disjoint because there's only one interior contour here. Okay. So, how does this work? Well, in order to actually apply this theorem, I need to change the orientation of C sub 1. So rather than considering C sub 1, I need to consider minus C sub 1, which is the exact same curve except the orientation is going the other way. So it's minus C sub 1. It's going to be the exact same curve except now my orientation is clockwise. Okay, so applying this to minus C sub 1, I can do this Cauchy-Goursat for multiply connected domains. And when I do that, I have that the contour integral along the exterior contour C sub 2 of f of z dz, plus we only have one single interior contour now. This is the integral, the contour integral over minus C sub 1, right? That's the curve we have to use in order to apply this modified Cauchy-Goursat of f of z dz is equal to 0. Okay, so there's my modified Cauchy-Goursat. But what is this? Right? This is the integral C sub 2 over f of z dz minus, right? The integral over minus the curve is minus the contour integral over the curve that's positively oriented. That's exactly what we want. And so these two contour integrals are equal. Okay. This might not seem like that big of a deal at first, but this is actually a really, really, really nice fact. Okay, so to see that, note in this example, we can use this so we can use the principle of deformation to compute the contour integral of 1 over z dz, where C is any simple closed contour that contains the origin. To see how we do this, let's take C to be this thing. here's my C. All right. Okay. Well, the idea is let, say, C sub 1 be the circle modulus of Z is equal to something. We'll call it R sub 1. That is small enough that C sub 1 is interior to that is interior to C. Right. Okay. Now, if the C is, say, positively oriented, the typical representation of the circle, of course, is positively oriented. I am choosing the C sub 1 to be a circle that is small enough that it is interior, right, entirely to that curve. So here's my C sub 1. It's some tiny, tiny circle. But we actually already know what the integral of 1 over z dz is if we have some circle centered at the origin. We've computed this because in our example where we computed this, it actually didn't really matter what the radius of that circle was. We could do the exact same thing, and we found that this is 2 pi I. But of course, this tiny circle also is positively oriented naturally, right? And so by the previous fact, by the principle of deformation, the integral over the contour C of 1 over z dz is equal to the integral over the contour C sub 1, this tiny circle that sits inside it. So it's 2 pi I. Okay. All right. And you see, we come up with more and more ways of getting around the definition of contour integral and being able to compute these integrals for nastier and nastier curves using these very strong conceptual facts that we have going for us. Okay. In general, how's the principle of deformation used? So in general, the principle of deformation is used like this. The idea is we have bad curve. We have bad curve C. Okay. We'll call it C sub 2. This is my bad curve. I have good curve here. Right. So if I am lucky enough to be in the setting where I have a function f that's analytic along the bad curve, analytic along the good curve, and analytic at all points in between, then the integral along good curve, or I should write this in the other way to show you the way that this is typically done. The integral along bad curve of f of z dz is actually the integral along good curve. Notice I didn't talk about orientation here because as we saw, it's not the biggest deal as long as we keep track of it and we're careful, right? So if we take both the bad and the good curve to be positively oriented, then the integral along bad curve is equal to the integral along good curve. Why do we have the name principle of deformation? The idea, and I said this when I first stated it, is that we can continuously deform we can continuously deform the curve C sub 2 into C sub 1. Now, again, to bring up topology, this is something that you talk about a lot in topology. This is one of like the main notions that you talk about in topology, of the notion of continuous deformation. But what's important is not that you can do this, okay, because that would actually allow us, we would have a lot of free reign here if this was all we needed. But we can continuously deform C2 into C1 in such a way that the deformation happens on a region where F is analytic. Okay. So that is the reason why we require our function to be analytic at all points in between. The way you can think about this is that we are we are like deforming this curve into the good curve. But this deformation is happening through a region where F has to be nice. If F is not nice, then on this entire region, there's issues with this argument. But the idea is that if F is nice throughout this entire region, then we can turn this outer curve, continuously deform it into the inner curve, and since we're doing this on a region where F is nice enough, this is not a problem. Okay. So this is why it's called the principle of deformation, that you have this fact that contour integrals along curves that can be continuously deformed into the other curves, those contour integrals are the same so long as F is analytic on both curves and analytic everywhere in between, okay, where this deformation is taking place. Okay. So this is the context usually and where this comes up. Okay. All right. So now we come to like a defining thing. Right? You can't be said to have had a proper course in complex analysis until you've mentioned this theorem that I'm about to state. So the following theorem marks a huge milestone in any complex analysis course. This is called the Cauchy integral formula. Okay. So what is the Cauchy integral formula? So let F be analytic everywhere inside and on a simple closed contour C, positively oriented. If C naught is interior to C, that is, Z naught is any point interior to C, i.e. is any point interior to C, then the value of the function at Z naught is equal to 1 over 2 pi I times the integral over C of f of z dz over z minus z naught. Okay. This is the Cauchy integral formula. Okay. What does this say? So first of all, there's an alternative form of this that can be used to actually compute some of these integrals using the Cauchy integral formula. So another way that you'll see this written is that the integral along this contour of f of z dz over z minus z naught is equal to 2 pi I times f at z naught. So either of these could be called the Cauchy integral formula. What does it say? Other than like the specifics of the formula itself, what does it mean? It means that if f is analytic on C and at all points inside, so if f is analytic on C and everywhere inside, then the values of f inside C are completely determined by the values of f on C. Why does this say this statement? Well, I'm saying that I can compute this, I can actually write out the value of f at any interior point by computing a contour integral, okay, of this integrand that involves f and then this term z minus z naught in the denominator here. But this contour integral, right, really, if I'm just thinking about the definition of contour, that only involves values of f along the contour C itself. Right? And so this quantity on the right, 1 over 2 pi I, that's just a constant. This quantity on the right, then, is a quantity that only depends on the values of f on that contour C. So my right-hand side quantity doesn't depend on anything except values of f along the contour C. Okay. This is this is actually pretty amazing here. So how does this work? Okay. So how does this work? Let's do a quick example here. So let C be the positively oriented circle. Modulus of Z is equal to 2, our favorite. Right. Note that if we have the function f of z given by, say, z over 9 minus z squared, the only zeros of the denominator are plus and minus 3. Those lie outside this circle. And so this f of z is analytic on C and its interior. Okay. Okay. All right. Also note that minus I, z naught is equal to minus I, is interior to C. Thus, if I want to compute the contour integral of z dz over 9 minus z squared times z plus I, using the Cauchy integral formula. Let me bring it back real quick. Here's my Cauchy integral formula, written in this way. If I want to compute this, this is 2 pi I times f of z naught. So this is 2 pi I times f of minus I. What is f of minus I? This is minus I over 9 minus minus 1. So this is minus I over 10. So this is, so this is equal to 2 pi I f of minus I. So this is 2 pi I times minus I over 10. So this is pi over 5. I times minus I is 1. Right. So there's one quick use of it. Okay. Which is pretty cool, because how would you go about trying to compute this contour integral otherwise? Right, it might be pretty nasty. But with the Cauchy integral formula, this is no issue. Okay. So already this gives you a really, really wide class of expressions like this that you can now compute contour integrals of using the Cauchy integral formula. Okay. Now, how do I actually prove this this fact? So basically, the idea here is that I want to draw a picture. So proof. I'm going to skip the proof of this mostly. That I'm going to leave this to. So most of this happens on page 165 in the text. The idea here is going to draw a picture that now you will recognize as familiar, where I have contour C positively oriented, okay, and I consider the point z naught, where I'm wanting to compute this value of f, to be an interior curve here of some radius. The textbook uses rho here, and this is c sub rho here, positively oriented. Okay. So I've chosen this radius to be small enough so that this circle is inside the contour. In question, of course, we can always do that. And the reason for doing this is that this quantity, f of z over z minus z naught, is now analytic on the curves in between them, on the C rho curves in between them. Okay. And so this allows us to follow principle of deformation. It implies that the integral along these curves, are equal. These contour integrals. So the integral along C of, say, f of z dz over z minus z naught is equal to this integral over this C sub rho, this tiny circle around z naught of the same thing. Okay. Okay. And so the idea here is that now we want to write the following. So now that we've used principal deformation to get that these two things are equal, this allows us to write f of that the integral over c of f of z dz over z minus z naught can be written as, or I should say, if I subtract from this, say, the constant f of z naught times the integral over c sub rho of 1 over z minus z naught dz, this can be written as the integral over c sub rho of f of z minus f of z naught over z minus z naught dz. Okay. All right. But then it turns out that we actually know how to compute this integral over this tiny curve of 1 over z minus z naught dz. What do you think that is? This is just a shifted. This is shifted version of integral over circle centered at origin of 1 over z dz. So this is actually 2 pi I. And this is exactly going to be where that 2 pi I comes from. Okay, in the expression. And so going back here, this then is 2 pi I. This is 2 pi I. And so this means that we have the integral over our outer contour C of f z dz over z minus z naught. This minus f of z naught times 2 pi I is equal to this expression, the integral over this small circle of f of z minus f of z naught over z minus z naught dz. And so now idea, compute or look at bound using our method where we talked about bounds. So look at bounds of the modulus of this contour integral. Okay, using the methods that we did a couple days ago, and show that this goes to 0. Okay. So if that goes to 0, then looking at this, what we have is that the integral over our contour C of f of z dz over z minus z naught minus 2 pi I f of z naught is equal to 0. Okay, and we're done. So there's some details to fill in there. But this is the sketch of it showing how all these ideas kind of coalesce. Right. So everything we were doing kind of worked together to lead us up to the principle of deformation. We used that immediately to say that actually these two contour integrals were going to be the same. Once we had that, then it was just a matter of applying this this computation of bounding the contour integral as we did a few sections ago. Okay, and this does it. This finishes it. Okay. Okay. Now, there is an equally important version of the Cauchy integral formula that we're going to call an extension of the Cauchy integral formula. But when we talk about the Cauchy integral formula, we're typically not going to make that much of an effort to differentiate between them. Pun intended. as you'll see here, why that's a pun. But there's an extension of our Cauchy integral formula that can be applied to actually give us an integral representation for derivatives of the function, not the values of the function itself. And so it turns out that the Cauchy integral formula can be extended to give us a representation in terms of integrals, in terms of an integral of derivatives of f at z naught. This is really, really nice because this is going to give us all of those nice facts. Okay, this is extremely nice because this is going to allow us to prove all kinds of amazingly nice facts about derivatives of analytic functions. Okay. Okay. So, what is this formula? So, I may go back and justify why this works out the way it does, or I may upload it as a quick supplemental video to illustrate the proof. But so maybe I'll say proof to be uploaded in supplemental video. As part of, I'll tell you what, we'll do it as part of next time's office hours, which are happening on Monday. Okay, so you can wait until then to see the proof of this fact. But what is this formula here? Okay, let this notation denote, so this is the nth derivative of f, right? Denote the nth derivative of f at z. Right, note the zeroth derivative by convention is taken to be the value of the function itself. The extended Cauchy integral formula, maybe I'll write it on the next page. So say that we use this familiar notation, right? You might remember that from Taylor's theorem or from any time you were coming up with theorems involving nth derivatives. Okay. The extended Cauchy integral formula is the following. If f is analytic on a simple closed contour C, and at all points interior to C, C is oriented positively, okay, and if z naught is interior to C, then it turns out that the, or maybe I'll write it like this, that the integral over the contour C of f of z dz over z minus z naught to the n plus 1, this is 2 pi I over n factorial times the nth derivative of f at z naught. Notice that when n is equal to 0, this is just the usual Cauchy integral formula. 0 factorial is 1. All right, so note. This is the usual Cauchy integral formula. Okay. How could this be? Well, we're going to see that, like I said, in the proof of this that I'll do on Monday. We'll see exactly how this works out, but take this for granted for now. What does this tell you, right? What does this tell you? Another way of writing this, of course, is that the value of the nth derivative of f is similar to the value of the functions itself, determined by the values of the functions on this contour, right, in some way. And so that way is seen as this is n factorial over 2 pi I times the integral over c of f of z dz over z minus z naught to the n plus 1. Okay, so whether you've written it in either way, writing it this way, like I says, lets you say the value of the nth derivative at a point interior to the curve is actually determined by the value of the point, or the value of the function on the curve in some way, or the integral of this expression. And so this is extremely weird if you're thinking about, if your baseline is real analysis. This is a very strange concept because, and you'll see exactly, why. Because we're going to use this over and over and over again to show so many things about analytic functions that are simply, just not true if you try to think of the analogous thing in real analysis. Right? We've already seen a lot of examples of that, but we're going to see plenty more. Okay. All right, so here's my extended Cauchy integral formula. So maybe I'll do like one example. And then we'll be done. Okay, so let's do a quick example of applying this. So if C is positively oriented unit circle, okay, and f of z is e to the 2z, then the contour integral of e to the 2z over, say, z to the 4th, right, dz, is, I can write this as the contour integral, of course, of f of z over z minus 0 to the 4th here, right, which is 3 plus 1 dz. And so this is viewing 4 as 3 plus 1. This is 2 pi I over 3 factorial times the third derivative of f at 0. The third derivative of f at 0 is 2 times 2 times 2 e to the 2z, so that's 8 e to the 2z. So let's think. So this would be 2 e to the 2z 2e to the 2z would be the second derivative, and then 2e to the 2z, so that'd be that would be 8. Yeah, so this would be 2 pi I over 3 times 2 times 8 here, so this would be 8 pi I over 3. There. So what's a unifying theme here? Once we have these fancy once we have these fancy integral formulas, a unifying theme here is we want to try our best to never actually brute force compute a contour integral the rest of our lives, right? So once we have these really, really nice facts, we just want to maximally avoid having to actually compute in the way that we did when we started out, especially, right? We want to avoid having to use the definition of contour integral to do anything. We are very content to use all of these fancy tricks and never have to do any actual computing. Okay, we are very happy with that. Let's do one more example. So let z naught be any point interior to positively oriented simple closed contour SCC C. Okay. When f of, say, z is equal to 1, so take f of z to just be the constant function 1, this shows that the contour integral over c of 1 dz, right, over z minus z naught, this is 2 pi I. Okay. And the contour integral over 1 minus, 1 over z minus z naught to the n plus first dz is equal to 0. Why? Because when I take derivatives of this constant function 1, I get 0. And so all these must be 0. And so this is true when n is 1, 2, 3, and so on. Right? But this is exactly what we've computed already, right? This was exactly our example of the bit about antiderivatives. This doesn't have an antiderivative everywhere it needs to, and this does, right? So note, compare this with our facts about antiderivatives. Okay, we've already actually shown this. Okay, but it's nice to know that these things line up in this way. Okay, so I'm going to prove some facts about like what comes next with the Cauchy integral formula. So this is going to allow us to prove a lot of these facts that I've been citing throughout the course, giving you examples of how complex analysis is different than real analysis. We're finally going to be able to prove those things. So all these big named theorems like Liouville's theorem, and some of these nice facts, fundamental theorem of algebra, these nice facts about an analytic function having derivatives of all orders. That is something that I'm going to be able to do thanks to this Cauchy integral formula. And then we're going to go from there to a discussion of power series, and you'll see how you'll see the interplay between an analytic function. Right at the very beginning of the course, I mentioned that we were using that word for a very specific reason, because if you're coming from real analysis, being analytic means you have a power series expansion in a neighborhood of some point. That's going to be true for us. But now the series that we're going to be dealing with are going to be complex valued series. So when we talk about a power series, it's going to be a power series of a complex variable. Not much is going to change. You're going to have basically the same tools for dealing with series that you always had, all the way back in Calc 2. But it's going to turn out that yes, analytic functions have power series expansion, and we're even going to have Taylor's theorem. Okay, so we're even going to have Taylor's theorem, and we're going to see how that leads into a discussion of something that is going to be different called Lorentz series. And ultimately, we're going to, culminate all this discussion uh, the residue theorem. So applications of all of this stuff to what are called residues. That is dealing with singularities and poles of functions, and how to compute integrals of functions that are naughtier than these analytic functions that we're talking about. Anyway, okay. So that's the roadmap for the rest of the course, pretty much. So that is that for today. I will see you all on Monday. I'm going to have office hours. I'm going to post homework 5 later today. It'll be due on Monday at midnight, so be on the lookout for that. Anyway, I will see you all later.